thing. Did I show you that yesterday?
No.
Okay, then here, I'm going to show you that now. Inertia. What we're going to learn today is I need to show you just this one demo about inertia. There's a second demo that I'll show you, but not today, on another day. So I'm going to show you the inertia demo, then we're going to learn about Newton's second law of motion, F equals ma, the most important equation in the entire universe, F equals ma. And then we'll learn about equilibrium, the special situation where the net force is zero. These are the three things we're doing. Here comes the inertia demo. Okay, this mass has inertia. It is presently at rest. How does it want to remain? At rest, yes. So I'm going to snap this card, and this card's going to go out really, really fast. What's this mass going to do? It's going to fall in the beaker, right? Here, watch and enjoy. 1, 2, 3, snap! You guys okay with that? It fell into the beaker, okay? It fell into the beaker because it wants to remain at rest. Now, Newton's first law of motion says an object is going to remain at rest unless what?
Unless the force is applied.
Yeah, unless there's a net force applied. So this guy didn't have to stay put, right? Let me ask you this question. I am now going to put a piece of tape on the card. I put a piece of tape on the card, and then I'm going to put this here. When did you leave?
Bathroom. I let him go.
You, oh, okay. That's fine.
You had your back turned.
That's okay. And so then I'm going to put this mass on the tape. And now I'm going to snap this card. Tell me, is that mass going to go into the beaker?
No.
Most likely not.
Yeah, probably not, right? Because although it wants to remain at rest, if I impress a force on it, it's going to move. You see? Here, watch this. 1, 2, 3. Okay, well, that was okay, I guess. I would prefer if it went really fast and hit Gavin right in the eyeball. Let's try that again. Shooting for Gavin's eyeball. 1, 2, 3. Okay, well that went okay. But you'll notice neither time did it fall into the beaker because now there's enough force. The card is exerting enough force on that mass so that the mass goes along with the card rather than the mass just remaining at rest and then falling into the beaker. Okay. Well, here comes Newton's second law of motion. The first law was an object at rest and stays at rest, an object in motion stays in motion unless that's taught by net force. Here comes Newton's second law. Newton's second law of motion says net force equals mass times acceleration. There it is. If you want to have it in symbols, F sub net equals ma. And the force is a vector and the acceleration is a vector. So I'm going to put the little vector symbols on them. Alrighty. Here's the sort of thinking that went into Newton's second law of motion. I've got a cart here. This cart is going to have a 500-gram mass in it. And I'm going to tie a string to the cart. There we go. And now on the other end of a string, I'm going to put a mass. I will put a 20-gram mass. I'll put a 20-gram mass on this string, and it will pull this cart across the table, hopefully. Yeah, let's find out. Here we go. Please watch as the cart accelerates. Pretty slow. You guys okay with that? Pretty darn slow. That's because I was pulling the car with the weight of this 20-gram mass. Tell me, instead of 20 grams, what if I used 50 grams? Instead of 20, I use 50 grams. What's going to happen to the acceleration of that cart?
Faster.
You guys agree it's going to go faster? All right, let's try it. So, here we go, 50 grams. Yeah, let me get this back again. Are you guys okay that that was noticeably faster? Okay, great. Well then, instead of 50 grams, how about 100 grams? How's it going to go now? You guys thinking faster still? Yeah, it's going to accelerate with a greater acceleration because I'm exerting more force on this. Here, let's go ahead and do that. Here we go. Whoops. Okay, 1, 2, 3. You guys okay that that was faster?
Yeah.
Great. And then instead of 100 grams, what do you think about, instead of 100 grams, what do you think about 200 grams? It'll go even faster still. In fact, it'll go so fast that if I don't catch it, the universe will explode. Here we go. 1, 2, 3. So you guys okay with that? So by doing these sorts of careful measurements, Isaac Newton discovered that the acceleration of an object is proportional to the force on the object, okay? Acceleration is proportional to the force. I double the force, I double the acceleration. I triple the force, I triple the acceleration. And then he set about trying to figure out the relationship between acceleration and mass. Here, Pooja, please sit in this chair, if you don't mind. I'm going to exert a force on her and accelerate her. Okay? Tell me, how do you suppose she will accelerate? Why fast? Why do you think Pooja would accelerate fast? Okay. Well, it can't be me. It has to be someone else. So, Izina, go ahead and come over here. And give her a little push. Okay, good. Okay, you guys okay with that? She accelerated pretty easily. Okay, go ahead and get up. Thanks, Pooja. Give Pooja a hand. Wait, Izina, you're on top. Now, I'm going to sit down in this chair. Now, this chair rolls pretty easily. I put new casters on it at the beginning of the year. So she should be able to roll me as easily as she rolled Pooja, right? Go for it. Well, did you exert more force that time? Yeah, a lot more force. But if you exerted the same amount of force, exert the same amount of force on me that you exerted on her. Yeah, not so much, huh? Thanks a lot. Give me Zena here. That no matter how easily rolly that chair is, the fact that I weighed a lot more than Pooja, the fact that I had way more mass than Pooja made it harder for her to accelerate me, regardless of how rolly the wheels are. You see? So I just want you to see that as well, that Isaac Newton discovered that acceleration is inversely proportional to mass. The more mass something has, the harder it is to accelerate the thing. You see? And so he just put these two ideas together and made it into an equation. Acceleration equals force over mass. But we in high school, we do not like fractions, so we multiply both sides by m, and we get ma equals f, and that's how we get f equals ma. But I just want to tell you, it's comprised of two separate thoughts, that acceleration is proportional to the impressed force, and acceleration is inversely proportional to the mass that you're trying to accelerate.
Mr. Shana?
Yes?
Something's flashing on here.
What is it saying?
It says 0 minutes, and it looks like it. I don't know what this means.
0 minutes? Did I run out of stuff?
Did you? Because like there's a